Okay, this is a thermochemistry. My name is Professor Chang Yu, and this is a pre-lecture video recording for my student in my section. And I'm going to continue to talk about, and then this is something about the internal energy change versus enthalpy change, and has something to do with constant volume process or the constant pressure when the system is under this. And practically you will see a lot of literature data is talking about enthalpy based on the change in terms of heat of reaction, because typical reactions are under constant pressure. That's a typical reaction condition. And also we're going to talk about something called Hess Law, and this is just taking the fact that delta H is a state function, and you want to take the advantage of the fact that that's being a state function, and you want to calculate the heat transactions or heat changes on various reactions. Okay, so let me talk about the work involved with the gas expansion. And you can think about the piston, and this is a piston, and this is your system, and you have an initial volume. And think about this is an engine in your car, and once this is an initial volume, and then this will expand, the piston will expand to have a new volume V2, and obviously expansion happens. And we have a very simple formula to explain what is a work done by the system. So this is a system, we're changing the volume, and then this piston is moving against what is called the external pressure. So the piston is moving against the external pressure, and we'll say the work is done against an external pressure. So and there's a negative sign, and the final volume minus initial volume. Now we are going to say external pressure is, we're going to see as a constant pressure P. So now minus P and multiply by delta V. So now you start to notice that work is minus P delta V, and for the extension this is a positive. Pressure is always a positive number, so therefore for the expansion case the work is negative. And what's the meaning of this negative work? And this has something to do with the notation of what we develop. As I talked about in my pre-lecture in the part 1, let's say this is a system, and this system is doing the work to the surrounding, and that's a negative work. If the work is done onto the system, that is a positive work. In other words, if the delta V is negative, we call that a compression. If you compress the piston, that means your work, which is the minus P delta V, is positive, and so the work itself is a positive work. So this has a good example of where the system can be defined, and then the work sign is very important for you to understand for this. For the little details about the work, saying that minus P delta V, in terms of the unit, let me say this pressure is a force per unit area. That's a unit. Volume changes cubic meters, So therefore, this one has a unit of Newton times meter, which is same as what we call the joule. So this is a relationship that it can be explained. So how can people essentially measure the internal energy change? And this is something has to do with you have to define the system. There are two systems. One is system of constant volume. Constant volume we also known as BOMB. It's like a bomb reactor or a bomb system. So what it means is, let's say you have a system that is a fixed volume, and so there's no volume change. So delta V is inherently zero. So this is a constant volume system, and this system, only thing that they can do is heat can go in, heat can go out. Right? So therefore, if you first law thermodynamics, internal energy is Q plus W, and there is no work is involved, and so therefore, if you know how much of the heat that we put it in on the constant volume, so we are using the symbol QV, that is the same as internal energy change. So now you are using something that is a fixed container, fixed volume container. You supply this amount of the heat, and then that is continue to use it as something that has a internal energy change, and that's what we call the BOMB calorimeter. Okay. So that's something give a convenience of measuring the volume on the fixed volume, measuring the heat, that all used to increase the internal energy or decrease the internal energy depending on whether you supply the heat or you take the heat out, and the delta energy of internal energy is going to be affected by this. There are other systems which equals system of constant pressure, and this is a most cases a real common system. So this is a case where now one of the good example is, let's say this is your system, but they are having a movable wall, just like a piston that we explained in the previous pages. So this system is experiencing constant external pressure. You just circle the P, and this is your system of your interest, and we want to know how the heat is going to be supplied and how this delta E is changing. So in this cases, if you're looking at the first law thermodynamic equation, internal energy can be described by heat transaction and the work transaction. This means you supply the heat on the constant pressure is going to be same as internal energy change minus W. In other words, if I just involve with a gas expansion, and that will be plus P delta V. So that's the one that we have a new system where we are going to redefine this another function, which is based on the internal energy and the pressure times the volume, and we give a birth to the new equation. Okay, so in the previous page I explained to you that heat supply on the constant pressure is delta E plus P delta V, and then we can redefine this one as a new state function, just as we use this notation, heat supply on the constant volume, that's a bomb calorimeter, that's the delta E. So whether the system is fixed volume or the fixed pressure system, you have a different notation. So they come up with a new quantity called H. We call the enthalpy. This enthalpy, and the enthalpy now defined as generally internal energy plus pressure times the volume. So this is a burst of the new state function. We call enthalpy. And now let me show you some of the typical reaction. Let's say I'm doing the reaction in a beaker, in a flask, and I'm putting an A, mix it in B, and this is under. But this system of my reaction mixture experiencing the constant pressure. So therefore, this reaction changes usually can be best described by enthalpy of heat of reaction. And also the way that people measure the enthalpic changes, this is a constant pressure, the calorimeter. So you have your system, you have a kind of the loose cover, you put your thermometer measuring the temperature change, and you have a supply the heat while taking the reaction takes place. So this system is under constant pressure. So therefore, delta H heat reaction is typically associated with constant pressure, and this is given out by reaction by the heat. So unless you're using this enclosed system, your reaction heat is going to be best described by enthalpy of reaction. Okay, let me talk about the Hess Law and the heat of the reaction. Let's say if I have a compound A plus 2B reacts and they become C, and then eventually they becomes a 2D molecule. So this is just a way that I had the reaction happen in a series of sequential steps. And the first step we call delta H1. Second one is delta H2. So overall reaction which is A plus 2B goes to 2D, and I would say C is what we call intermediate. Right? So I want to know the delta H reaction for that. But in the tabulated form, this process is well defined. The second process is well defined. Then I can usually say delta H reaction, which is the change of the state function final minus state function of initial. So therefore it is a series of summation of first delta H of reaction in the first set and second set of delta H reaction in the second set. So this is taking the fact that we are having this Hess Law is an example of, by summing all this reaction involved, we can essentially have a predictive knowledge on final products. So let me show you an example of using the Hess Law to predicting this the following question. Let me write down the questions. So here are three examples of reaction. We know exactly the delta H reaction value for the corresponding reaction that was written on the left hand side. And the nitroxide become NO2, nitrogen and oxygen meet with HNO3 with the nitric acid, and nitrogen and oxygen gas meet with the nitrogen monoxide gases. And those are the three examples. And so then the question that people wants to know is the reaction, what we call the 3NO2 gas react with H2O liquid becomes 2HNO3 aqueous plus NO gas, and they want to know what's my delta H reaction. They put a little circle there because the circle means it's just a standard state, which means on the ambient conditions such as one at room temperature and atmospheric pressure. So they just have to define the temperature and the pressure for this certain condition. So now question is, what is my delta H reaction for this particular reaction using the three equations above? So let's see which one shown up in here. So first NO2 gas, which is a 3NO2 gas, but the quantity that I have shown up, NO2 show up on the right hand side, and this is a delta H of this. So I want the reaction shown up in a way that I need to write 3NO2. So what that means is I want the equation writing in a reverse way. 2NO2 becomes 2NO plus O2. And so that's a reverse reaction. So this first reaction in the happening is we write it as minus with another minus, which is a 116 kilojoule, right? But still I don't get this number that I want, so then I want to multiply this one by a number, and that number has to be multiplied by 1.5, and this make this portion to be matched with the one that I have and from the first equation. So what I want is I want to keep this number to be multiplied by 1.5. So as far as I'm concerned, the first set is done. So let me look at the second set, which has something to do with water. So now water is showing on here on the left hand side, and I'm looking at the water which is showing up here, which is on the same side. So that's good. So I'm going to rewrite this one, 2N2 5O2 2H2O becomes 4NHO3. In that case, for the second reaction, I'm keeping the number as it is, 256 kilojoule with the same sign of negative here. And once again, I just have to correct for the right amount of the constant. So here I only see the number 1, whereas I only see the number 2. So what I have to do is I have to multiply this one by 0.5 to make the constant in front of the water to be 1. Right? So then this value has to be corrected by multiplying by 0.5. So far I have the use of first and second equation. I'm left with, and if you're looking at HNO3, and that is shown up correctly, and by multiplying by 4 times 0.5, that's going to be 2. And the last one that I have to deal with is the third equation that is shown. And let's have a look at that, right? So you have NO2 here, NO, but you are having 2 times NO2. So same drill. I am going to, first of all, I have a product side is nitrogen monoxide. So I am going to write the third equation, N2O2 becomes 2NO, and there will be delta H will be the same value plus 183 kilojoule. But now I have to just once again correct for the different constant shown up. So which is, let's say this is I only need NO, so therefore this whole equation should be multiplied by 0.5. So therefore I'm going to do this one by 0.5. But I start to see some problem here, because when I see just considering this NO, this NO shows in the first equation as well. So the last thing that I did, I cannot apply easily right away. First, I have to deal with these two equations first to write the corresponding equation, and then how am I going to use the third equation for myself. Okay, so let me rewrite what I wrote here. And so the first, talking about first equation and the second equation one more time. Okay, so I copied down from previous slide, and then let's deal with this first and the second equation that I shown up. So let's say the 1 plus 2 will give me 3NO2 becomes 3NO plus 1.5 O2. The second one will give me the N2 plus 2.5 O2 plus H2O becomes 2HNO3. So far that I have made it this two. If I add them together, I will end up getting 3NO2 and N2, and this one goes away, and you ended up having 1. So just a 1 O2, and then H2O becomes 3NO plus 2 times HNO3. Okay, so we haven't used the last one, which is showing up in here, and how we're going to use that to finally achieve this equation of our interest. So this is an equation of our interest, and shown up as water. There's a water molecules there, that's fine, and 3NO2, and this one shown up, and we want to have only one NO on the other side. Okay, so to do this, we need to use this equation that this N2 O2 has to go away, and 2 times NO. If I use the equation, reverse the equation of the third equation, which is let's say this is equation 1, this is equation 2, this is equation 3, and this is essentially equation 3 reverse. And if I using this way, I will add them together, and this 2 nitrogen goes away, and this nitrogen oxide goes away, and we will get the final equation as we need it. So the third equation should be a reverse on what we do, and finally we'll get 3NO2 and H2O water becomes nitrogen monoxide and 2 times HNO3. So therefore, reaction itself is a first reaction has to be multiplied by 1.5, and then also this one was in the reverse way, so it's a minus. And the second one, which is a second reaction shown up, this is the first one, this is the second one, was second reaction multiplied by 0.5, and then this is in the same direction as shown up, so we're going to use it as it is. And the third one is we're going to have a third reaction and use as it is, but has to be multiplied by -1, or the reverse direction. So I am going to say this is actually minus. Okay, so you're putting all these numbers down and you will get to the final delta H reaction, and that should be minus 137 kilojoule. The fact that delta H reaction is negative, that means it is an exothermic reaction. Okay, so let me talk about what is called the heat of formation, and this is the symbol that we use is delta H formation on the standard state. And there are many compounds that it is the pure. There are a lot of compounds that heat of formation was given and tabulated. One thing that you should know is heat of formation is defined to be 0 for pure compound under standard temperature and the pressure conditions. So for example, delta H formation of, let's say, carbon, graphite is typically a pure form of an element, and this is by its own definition is 0. And so other useful one is, what about the pure form of an oxygen, which is an oxygen gas under standard state? And so they are essentially pure elements, so therefore this is heat of formation is 0. So does delta H formation of aluminum, for example, that's a solid in the pure element form, that is a 0. But remember now, what about heat of formation of, let's say, CO2 gas? It is not pure element in standard form, so it is not 0. Okay, there's some numbers involved in for that particular one. So it is all the delta H F for any compound. Some of them is pure elements, so 0, but some of the compounds that is not pure is not 0, and all tabulated. Okay, so it's all tabulated, so therefore we can kind of using this relationship to figure out the number for a reaction that involves is the following a lot of products and the reactants. So this is a Hess law in a useful form. Heat delta H of the reaction is essentially summation of all the heat of formation for product, and there are n times involved, and then you just sum it and subtracted by heat of formation for all the reactant, and there will be some numbers involved. So this is a knowing the fact that you are involved with the reaction with series of reaction, and this is a Hess law application to figure out based on the heat of formation, you can essentially calculate out what will be my heat of reaction. So this is a Hess law application on this subject. So I will talk about more in my lecture on how to use this for estimating different kinds of reactions.